Hello, everyone. So, in this recording, I'm going to talk about chapter 4 in, in the course notes, and it's about Introduction to Cryptography. So, in this part of the course, we're going to look at the fundamentals of cryptography, and then later we will start moving into specific cryptography techniques. So, the idea of cryptography is not new. It has been around for generations. And the basic idea behind cryptography is that I need to exchange information with somebody else without that information being exposed or known to a third party, right? So armies for decades, millennia, they want to maybe coordinate to fight the enemy, and leaders want to communicate to their troops by sending them orders. But there is always the risk that the messengers will be captured and the message will be uh, in, intercepted and the enemy will know. So, this is where cryptography came to exist, right? To communicate between leaders, army leaders and their troops, or between the kings and emperors and their generals, and so on, right? In the modern era, we need to encrypt messages and communication to maintain privacy, to make sure that nobody else is looking at the information that we need to exchange, while there are still military and political applications for that as well. So the idea behind cryptography is to make sure that the information looks unintelligible or very hard to understand by a third party. If somebody looks at the message after it's encrypted, it doesn't understand anything from it, right? While we make sure that uh, both parties that are communicating, they know how to interpret that message. So the two ideas here is that we need a mechanism to take a message and make it look like it's garbage, look at random, right? While at the same time we have a way to retrieve that message back. A new a new application for cryptography nowadays, aside from being, the privacy thing, we also have uh, two more, or at least two more applications for cryptography. One of them is integrity checking. The integrity checking is responsible or dedicated to making sure that the message does not change, right? So the message itself may not be encrypted. I may, for example, send a message to the entire class saying that we should have a quiz on certain time, right? And I don't want the message to be changed by somebody else who is, for example, wants to maliciously change the time or change the location so that students miss the exam. So integrity check is a technique where cryptography is used so that we make sure that the message does not change, and if it changes, we know that we detect the change, right? So even though the message itself may not be encrypted and may be sent publicly, but we don't want it to be changed by anybody, right? Another application of cryptography is the authentication, right? Authentication is to verify that somebody or someone is actually uh, um, uh, authorized to access information or authorized to operate a system, right? For that, we need to verify their identity. So authentication is the term and cryptography is the tool that we use. Some common terminologies that we'll use in this course is plain text. We refer to plain text or clear text. Uh, that term refers to the original text before it's encrypted, right? Ciphertext is the distorted form of the text after we encrypt it. We call it ciphertext. So the process by which we take a plain text and convert it to ciphertext, we call it encryption, and the reverse is decryption. So decryption takes a ciphertext and return it to plain text. Cryptographers are people who create these clever techniques and methods and algorithms to encrypt plain text. And there are always other people who do the reverse, who are trying to take the ciphertext and decrypt it to um, turn it back to plain text. And we call those cyber analysts. The I guess the bad news here is no matter how clever the techniques are in cryptography, they always can fail. There is always some way that a third party can take a text, a ciphertext, and put it back into plain text. The history of the World War II, for example, shows us how the Allies were able to decrypt um, the the German um, encrypted messages using by discovering the keys and discovering their equipment, their machines. So there is always a way to break the encryption and retrieve back the plain text. But the idea is behind all cryptography is that if there are a lot of people try to solve the problem and they fail, then we can rest assured that the problem cannot be solved anytime soon, right? So we cannot have a system it's impossible to retrieve back or to decipher. There is always something that can be. There is always a technique that will give us the same or decrypt the message. But we'll try to make it, or cryptographers will try to make it hard enough so that it will take a lot of effort and a lot of time for people to decipher the message. And that's the basis or the tenet of cryptography, the fundamental tenet of cryptography. All right, so as I mentioned before, cryptography systems involve both a technique, an algorithm that takes a plain text and convert it into ciphertext, and a key. So these two components need to be there in any cryptographic system. So the algorithm will take the key, will take the plain text, and use both to generate the ciphertext. And then we can use the key and the algorithm again to uh, retrieve the plain text. Normally, the algorithm itself is well known. It's not a secret. People will know it and published. The key is the secret, right? And that's one of the reasons, one of the techniques that we will study in this course is the secret key cryptography, right? And we call it secret key because we need to keep the key secret. Um, Algorithms usually have certain difficulty or certain complexity that makes them take a plain text and convert it to ciphertext based on the key, right? Uh, One of the ways that uh, a cipher analyst try to break the code or break the encryption is by trying different techniques to discover how to retrieve the plain text. One of them is trying all possible keys. Right? So it is possible that somebody will say, okay, I will try all possible keys until I find the key that actually retrieves the plain text from the ciphertext. All right, so that means that if the number of keys, the possible keys, is small, well, the decryption will be easy. So we need to make sure that the key is long, or possibilities of the number of keys is quite large. So it will be very, very, very difficult for someone to take the brute force, we'll call it the brute force attack, where they will just simply try all keys. All right. So the simple example to illustrate this point is, let's say we have one of those locks, right? And the lock has, we'll call them the, locker locks or bag locks, that has a number, you know, the number, three-digit number, for example, that takes anything from 0 to 9. So if somebody wants to lock their safe, lock their storage, lock their bag, they will put a random number that they only them they remember it. So let's say 953. That's the secret number that I will keep to myself, um, and only me will know this number. So anybody else who tries to open the bag, uh, they won't be able to, right? But a thief may take this bag with the lock in it and start trying all the numbers from 000 up to 999 until they find the number that opens the bag. Right? You'll see in some of the spy movies or some of the um, action movies that people will try to open a safe by hiring an expert, and the expert will listen to the safe and moves the numbers. So that's probably not the brute force attack. That will be some kind of a clever way to discover uh, the key without going through all the numbers. But I could simply, if I get the bag, I can simply, with a little bit of patience and a little bit of time, I can simply try to go from 0000 to 9999. Right? So from probability, we saw that how many ways how many numbers out there. Right? So that's simply 10 multiplied by 10 multiplied by 10 will generate 1,000 different keys, 1,000 different numbers. One of them will open the bag, right? I can make it harder for anybody to open the bag if I add another digit. If I add another digit, so it will be 4 digit, then the total number for the total number of uh, different keys, so 4 digits will result in 10 to the power of 4, and that's 10,000. So here we can discover quickly that the longer the key is, the harder for someone to use brute force attack to discover the key. And that's why we will see later that the length of the key is um, one of the metrics that indicate how strong the encryption is, right? And also that justifies too the reason behind asking for complicated password. So nowadays, if you go to a website or an application and ask you to create an account and then set a password, sometimes the password will be dictated. Oh, you have to use capital letter, small letter, at least one capital, at least one small, a number, and a special key, a special character. Why? Well, you know why. So if I have, let's say, eight, if the application dictates eight character password, and all eight characters are from the English alphabet, so now we have 26 to the power 8. That's not by itself a small number, but we know that sometimes with the help of technology, with the help of computers, I can try these numbers very quickly. But if I say, well, you have 26 characters plus 10 digits, right? So now we have 36 different ways we can create 8 character password. If I add capital and small, so now we have 26 capitals, 26 small letters, and 10 digits. If I add another 10 special characters, so now you can see that this will result in a very, very, very big number of possible passwords, and it becomes harder and harder for anybody to guess them. So even if you, let's say, for 36 characters, 36 different ways to choose a character, and 8 characters password. So that's a large number. If you have a computer that generates one password in 1 second, it will take 36 to the power of 8 seconds to find the key. In fact, actually, because the key not always at the end, so we will find the key. So for brute force attack, the key can be found in half of, or about half of the time. So 36 to the power 8 divided by 2. So about half of the time, because sometimes the key is not at the end. So if you start with AAA, AAAB, AAC, you may hit actually the key early, or you may hit it late. So on average, you'll find it in half of the time, right? If you have a faster computer and it will take every trial, every attempt, half a second or 1/10 of a second, this time will be reduced significantly. So to combat that, okay, we need more digits. So instead of just 36, okay, so now 26 and 26, that's 52 characters between capital and small, plus another 20, that's 72 different characters to the power 8. So we'll have a longer time to go before we can uh, break the key or find the password using brute force. Now, brute force is one of the attacks, but there's also other ways, clever ways to discover the key without from the first possible key to the last one. we could, a lot of people use their pet names as password. So if I can guess somebody's pet name or use it, somebody will use their birthday. Some people will use uh, the word password 123, for example. Or so that's why the clever password algorithms now say, well, don't use uh, any word that can be found in a dictionary, because there are dictionary attacks where the hacker will try all the words in a dictionary, right? Or will create their own dictionary and will try all the common words for password. So you need to have this password as random as possible, right? Same thing for keys. For cryptography keys, you need to find a key that's as random as possible so nobody can guess it, and but still brute force attack will try to find it. Okay, so the general system for cryptography here, we will find variations later, but the general is we have this communication between the sender and the receiver. The sender could be a server, the receiver could be a client in our network applications. Um, so we can, the sender will have a plain text, will pass it through encryption algorithm with the key. Uh, the encryption algorithm, with the help of a key, will generate a ciphertext. The ciphertext will be sent through the network or through the communication channel. At the end, we have decryption algorithm uses the key, sometimes same key, sometimes a different key, as we will see later, to take the ciphertext and turn it back into plain text, and then the receiver will see it. Right? So that's the general idea. Now, for large text, what we do, we're not going to take uh, the whole document, a report, and pass it through ciphertext, or a cryptography algorithm. Usually we'll break it down into blocks, and the blocks, each block will be passed through the algorithm and then generates ciphertext. So we do block by block, right? Okay, we'll see all these details later, but let's now start with the simplest ciphers, simplest techniques that takes a plain text and convert it into ciphertext. So one of the earliest techniques for cryptography is attributed to the Roman Emperor Julius Caesar. And Caesar, what he did, well, they didn't use English at that time, but let's assume that they used English um, with the 26 letters. So what he did, he took the let's say um, a word like school, school, and say, well, I'm gonna substitute. So I have my alphabet A, B, C, D, E, F, G, H, I, J, K, L, M, P, Q, R, S, T, U, V, W, X, Y, Z. All right, I still remember the alphabet. Good. So I'm gonna take each letter and shift it by 3 positions. So S here, if it's shifted by 3 positions, it becomes V. And C, shifted by 3 positions, it becomes F. And I'll assume all capital letters for now, just to make sure that the example is easy. So school, CSHOOL. So VFH becomes K, O MPQR. So I forgot O somewhere. O here. Actually, I forgot two letters. LMNO. All right. So O becomes R, and L becomes O. So now this is the Caesar cipher. So now I'm gonna send this letter or this word, and nobody will figure it out, right? Because it's so encrypted now, nobody will figure it out. And that was Caesar's technique. Now, of course, in Caesar's days, not everybody knows how to write and read, and not everybody's clever enough to figure it out. So that was a reasonable technique for those days. All right. If I want to look at it from the mathematical point of view, right, and also, as we said, the algorithm and a key. So every cryptography system has an algorithm and key. So you can see that the key here is the shift by 3. The algorithm is shifting, and the key is number 3, right? So I can take any letter shifted by 3, I get the ciphertext. So, and that is explained or is uh, um, described by the formula that you see here. C equal P, which is the plain text. C is for ciphertext, so the cipher character equal P, which is the original character, plus K, which represents the key, mod 26. The 26 is the number of letters in the alphabet. And why we need the mod here, the modular, is because if I want to have Y in the original text, now Y, if I want to shift by 3 letters, we don't have enough 3 letters here, so we need to go back to B, right? So we need to convert it B. Another thing that I want to mention here is actually I'm representing the numbers, I'm representing the letters with numbers, right? So for this to work, I have to have a representation. So A, for example, will be represented by the number 0, right? And 0 plus 3 mod 26 is modular 26 is 3. So if this is 0, this is 1, this is 2, this is 3, then A will be replaced by D. All right? And to replace C, which is 2 plus 3 mod 26 is 5. So that's F. Right? So that's the mathematical representation of Caesar algorithm. I can use the same algorithm, which is shifting, and the same key to retrieve the original message. So how do I do that? Well, I'll take C, which is the ciphertext, minus K, mod 26. So in other words, I'm shifting back left, right? So for encryption, I shift right. For decryption, I shift left, right? By the same number. All right. Uh, as far as we know, Caesar used only one key, which is number 3. I think they weren't clever enough to change the key, or maybe it was difficult to change the key because it's a vast empire, and to change the key, the other side has to know the key as well. So they used one key, which is 3 all the time, right? But we can use different keys. Uh, we can use a Caesar algorithm with the key is 6. So now instead of replacing A with um, D, I can replace it with another number. So let's say K equals 6 here. So C, which is the ciphertext, equal P plus K mod 26. If I want to replace the school here, S has a number, so 6, 7, 8, 9, and this is 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. All right, so for S, that would be 19 plus 6 mod 26. So that's 25 between the two of them, right? 25. So 25 mod 26 is 25. And 25, the letter 25 here in the order is, that's 20. 1, 2, 3, 4, 5. So it's Y. So we can replace the word S with the word Y, or substitute the word S with Y, right? So we can change the key to have any uh, any key we want, right? One thing to note here, or two things to note, is that how many keys we have. We have exactly 26 keys because we have 26 characters in the alphabet, in the English alphabet. So one of them is not practical, so we'll say 25 keys. Why? Well, if I substitute A with itself, it doesn't make sense, right? So we cannot use, so if we want to substitute, we want to shift by 1 or shift by 2 or shift by 3. We cannot shift by 0. It doesn't make sense. So we have about 25 keys from 1 to 25 out of 26 characters. So we can shift by 1, which means A becomes B, B becomes C, and so on. Or we can shift by a large number. If I shift by 25, then A becomes Z, right? B becomes A, and so on. It rotates. So that's one observation. The other observation is actually I am substituting one character with another character, or one letter with another letter. So we will call Caesar cipher as an example of substitution ciphers. Substitution ciphers change one letter with another letter. Later on, years after that, actually closer to the modern era, um, I think it's French person called Vigenère came up with this idea of the Vigenère cipher. So he said that instead of shifting everything by a constant number, how about we shift things by a variable number? That means that in a letter or in a message, not all characters are shifted by the same number. Okay, so he came up with this Vigenère table. The idea is, so how we do this is written in these lines, but I'm going to explain it in the table here. So let's say the command is attack at dawn. Let's put this to the side here and put this here on the side, and So I want to send the command attack at dawn. One of the reasons we don't use spaces is because spaces and punctuations in general, dots and exclamation marks and semicolons and all of that, it will give hints to the uh, to whoever wants to decrypt the message. So we move the spaces. We don't give hints, right? So the command is attack at dawn. For Caesar, we just need to shift each letter by a constant number of positions. But with Visionaire, we will shift them by variable. So variable shift, each character will be moved by a variable uh, number of positions. So this variable number of positions comes from the key, from a key. And the key here is another word. We can choose other words. Here is the key is lemon. If the key doesn't match the message itself, we just need to repeat it multiple times until it matches. So here we replicated the lemon, lemon, lemon multiple times until it matches um, the original plain text. So now, if I look at the table to the side here, see that let's assume that the message is, or the row at the top represents the message itself, the original plain text, right? So A is shifted by L. So if I go down to L, I see that, so this is the columns, or actually the row in the first column, the rows in the first column here represent the key. And the columns in the first row represent the characters in the plain text. So we'll take A, we'll look down at L here. So we substitute A with L. Then we'll take T at the top and go down to the letter E. So the intersection between T and E is X. And if you have this table in front of you, you can follow me. So the intersection between T and E is X. So we'll replace that with X. The other T is shifted by M. So here is T again, and we go down until we reach M. So the intersection between T and M is F. So we write F. So notice here that these two T's are not shifted by the same number of positions. They shifted by two different positions. All right, so we can continue doing that, and we end up with LXFOPV, so the one that's written here. Right. What is the advantage of this technique? The advantage of this technique is, first of all, it's harder to find the key. In the simple cipher, simple substitution cipher that we saw with Caesar, I can just simply try to shift the characters one by one. So let's try to shift when I see LXF something something, right? I could say, okay, let's try to shift everything by one to the left and see if we can get the key. If it doesn't work, okay, let's try to shift it by 2 and see if we can get something. If we can't, well, let's shift it by 3. So we can try 25 different ways and eventually we'll find the key. Here it's much difficult because we cannot easily find the lemon. The key, it could be anything, so it's much harder. It's not impossible, but it's much harder. So the first technique is very susceptible to the brute force attack. Simply somebody will try all the possible shifts until it finds one. Another vulnerability in the previous technique is what's called, um, here we'll find it, where we do analysis, right? And notice that um, in some languages, English one of them, is some letters are used a lot or more often than others, right? For example, the common letter in the common used letter in the English language is E, right? So if I look at a large document and I count how many E's in there, I'll find that the E repeats more often than any other letter. So if I shift all the characters by 3 positions, right, and then now the cipher analyst doesn't know the key, but they can just do analysis and find what is the most common letter in this cipher text that we find, and let's find that it's R. So if the ciphertext has the most common letter R, and we know that the most common letter in English is E, then it's very likely that R is E, right? R in the ciphertext is E in the plain text. So now we know what the key is. So let's try the key, and we may have actually solved or broken the code without even trying the brute force, just by observing that some letters are, um, the characteristic of the language will give us hints about how frequent some letters are. With Visionaire, that's not entirely eliminated. Why? Because notice here that this uh, these keys are different, right? 1, 2, 3, 4. These are 5 different keys, but then they repeat again. So if somebody figure out what the key is, not necessarily figure out what the key is, but they figure out what the size of the key is, in this case is 5 characters. I know that this is shifted by the same number of letters as K, and W is shifted by the same letters as L. So they're all shifted by the same characters. And notice that they are actually, well, I didn't finish the whole thing, but they are shifted by the same positions, which is L, right? So if I isolate every fifth characters or every sixth character, now they are no different than Caesar, right? Every sixth character in the original text is shifted by fixed number of positions. So I can just split the big document that was encrypted into groups of 6 and apply the same analysis as I did with Caesar cipher. Right? So that's the vulnerability of Visionaire, but it is still more elaborate. All right. So let's go and look at more techniques that makes analysis more difficult. All right, if we go back to the notes here, one probably intuitive way to figure out or make things a little bit harder is to make the key matches the size of the message itself. So I said is one of the vulnerabilities of Visionaire uh, technique is that if somebody knows the key size, it becomes just a simple Caesar substitution cipher. It's just that it repeats every 6 characters. But if I make the size of the key matches the size of the message itself, then I eliminate this vulnerability. It becomes much harder to actually figure out um, or use the cryptanalysis techniques, because now every character is shifted by a different position, different number of positions than any other character, right? So actually we'll call this the one-time pad. So one-time pad uses a key that's exactly same size as the message itself, right? So actually this kind of technique is one of the strongest way we can encrypt the system, encrypt the plain text with, right? And it's considered one of the most difficult techniques to break. Uh, Now, why don't we just say, okay, that's one-time pad, let's do one-time pad for everything? One-time pad works well if the length of the text or the length of the key is equivalent to the length of the text. But the text sometimes is too long, it's a big report, you want to encrypt it, so you're going to create a length key is the same as the report. That's probably not very practical, because remember, you have to exchange the key with somebody, right? Somebody else needs to have the key so that they can decrypt the message. Another difficulty or another thing to watch is the one-time pad works fine if it's actually random. If the letters that in the key are random. Actually, the opposite is totally true. If you try to encrypt one English sentence with another English sentence, it's actually very weak encryption technique. So you will say, okay, let's take one paragraph and encrypt it with another paragraph. So these are two paragraphs the same size. Let's encrypt one with the other. Now, encrypting one English paragraph with another English paragraph is bad idea. The one-time pad works fine if the key is actually as close to being totally random as possible, right? So we will have this concept being repeated again at some time, maybe during the tutorials or exercises. All right. So both techniques are called substitution ciphers because they substitute one letter or character with another. Also, they're called monoalphabetic ciphers. Right? It's same called them monoalphabetic because they substitute one letter with another. Okay, a different type of ciphers is we call them transposition ciphers because they don't change the letters themselves, they change their position. Right? So rather than changing the characters, we keep them, just play around with their position so that we scramble the positions. Right? So this technique here, I don't think it's associated with anybody's name, but let's take the message. The plain text is called examples are fun. Let's write one. Right? Let's write one, and right here is misspelled. Right? It's missing a character. Right? So if I arrange this plain text in this table, so uh, examples are fun. Let's write one. So one of the reasons we misspelled right is to make sure that they fit 6 by 6. So we have exactly 36 um, boxes there, or actually 5 by 5, so 25 boxes. And now once we write the plain text row by row, I can now generate the cipher by writing column by column. So now ELEET, then XEFTE, and so on. So now the cipher text will look like this. Ciphertext, not completely immune against pattern analysis. Again, if you take this list and say, what is the most common letter here, right? And you may find that the most common letter is E, right? Um, we didn't actually substitute it anywhere. Um, so you'll find that, okay, so this means that we didn't really substitute any letters here, and we just moved things around, right? um, it gets even easier. I know that if I know that the ciphertext talks about the weather, right? Let's assume that the ciphertext talks about the weather. So I know that anybody who's talking about the weather, they may be talking about temperature or pressure. So I can try to find the word inside this. I know that it's probably scattered, but I can find it. Here, the word example, if I know that somebody is talking about examples, so I can try to find where is the letter example. So we have X here, right? And A here and M here. So I quickly figure out that actually there are 3 letters between, or 4 letters between every one, or so X, and then ignore the E, F, T, E, so that ignore the 4 letters, and then there's A. All right, so that's XA, and if I go backward here, that's E, so EXA, and forget about these 4, that's M after that. So now I figured out the pattern. I figured out that take a letter, skip 4 letters, take the second letter, skip 4 letters. So now I can reconstruct the original table and decipher the text. And this is probably one of the things that we will try in a quiz or in an assignment, where I give you something like this, and you will be able very quickly, in fact, to retrieve the original text just by rearranging um, the letters into rows and columns. Right? Okay, so let's see if we missed anything here. Okay, um, now I can be more clever and say, well, the transposition, the substitution by itself is weak and it can be vulnerable. The transposition can be weak and vulnerable. How about I combine the two, right? And this is actually what modern cryptography techniques do. They combine substitution and transposition, um, and the techniques that we have, they do both, and becomes much easier when we use binary. All right, so instead of using alphabet or numbers, we will use binary. And the binary, we convert all the data into binary, and not just text. We can take an image and convert it into a binary, ones and zeros, and then we encrypt the image by doing substitution and transposition. All right, one technique we can do that is by looking at, um, so we have here example of 4 characters, 4 bits, and we want to um, convert them into another 4 bits. So we want to scramble them, take 4 bits, the top, scramble them with 4 different bits. We can do that in different technique, but this is one of the techniques that uses decoders and encoders. For those who are familiar with binary um, digital circuitry and digital logic, we know what the decoders are. So a 4-bit number can generate 16 different combinations, right? We can represent 16 different combinations using 4 bits. So if I enter 0000 here, and if you're using LEDs, for example, so the decoder will light the first line here. If I put 0001, the decoder will light or turn on the second bit, and so on, second line, so on, right? So if I attach the decoder to encoder, which does exactly the opposite, takes any one of those lines and convert it to a number, and we somehow connect the inputs or the outputs of the decoder to the input of encoders, then we generate encryption. We scramble the bits, so any number of bits that enter from the top will generate a different set of bits at the bottom. We can represent that by a table. So we can have this plain text and this is ciphertext, right? So everything that was created here, so plain text 0000 generates the ciphertext 1000 and so on. So that's the encryption. We don't really need 2 tables really. So, but here there's encryption and decryption, right? So we can just look at the opposite. So the decryption here, if we take 0011, the ciphertext will be 1010. And if I look at it from the opposite, so the ciphertext will generate plain text, right? So it's the same. Uh, it's uh, it's the same. We can use one table to do the same thing. Um, Here, if we look at some of the math that we need, so for a block size, so obviously if I want to encrypt a larger message, I have to take the message, convert it into binary, and then take 4 bit at a time, right? Because I cannot have a decoder that is infinite number long. So I have to make it small. So the decoder could be 4-bit, could be 8, could be 64. In fact, the bigger the decoder is, the better, right? But I have a limitation. The decoder could be 64-bit, could be 128-bit, could be 256, 512, but it's still limited in size. So in this example, we just need to illustrate the point using only 4-bit decoder. So for a block size of n, where n is 4 in this case, we will have 2 to the power n, or 2 to the power 4. That's 16 possible different plain text blocks, right? So each one of them can be converted into another 4-bit block. So obviously, if I increase the number n, I will have more possible or bigger plain text blocks that can be converted into also big ciphertext blocks. So, and that's obvious, or the benefit of this is obvious, because for 4-bit plain text, there are only 16 possible ways. So it is possible for somebody to try to figure it out, right, by trying 16 different combinations. But if I have 64 bits, that becomes a lot more difficult. Right? So again, that's another example of why we need large size blocks or large size keys. Okay, we'll see here that for block size n, the number of distinct reversible transformations is equal to 2 to the power n. All right. So now we have um, for 4 bits, we have 16 different ways we can take a number and convert it to another number, right? So we can take 000 and convert it to 1010 as a cipher. We can take 000 and we convert it to 001. We can take 000 and convert it to 1110. So we have 16 different ways we can do that. Now, if we take from what we learned about permutations and combinations earlier, so if we take the 000 and convert it to another 16, another 4 different bit combinations, what we end up with is now the first 4-bit can be converted to any of the 16 possible ways, but the second set of bits can be converted into only 15, and the third set of bits can be converted to only 14 because the first two were taken, right? So the total ways we can convert 4 bits, or we can generate ciphertext from the 4 bits there, is 2 to the power 4 factorial. Here 16 multiplied by 15 multiplied by 14 multiplied by 13 and so on, that's 16 factorial, right? And the 16 factorial is actually 2 to the power 4, right? The 4 bits. So for 4-bit, we can have 2 to the power factorial ways to generate ciphertext. Now, if we have 8 bits, that becomes 2 to the power 8 factorial. So that we'll see here that the more bits, the more ways we can do that, and the harder for somebody to figure out how to decrypt the message. Okay, but the problem with the increasing the size, that we need to have a memory to save it, right? How can we figure out? We know that we have all of these ways to convert a 4-bit to another 4-bit. But to decrypt it, we have, first of all, to encrypt it, we have to have a table. We have to have a table like this, right? I said there is no need for two tables, so just one plain text and one ciphertext. So to to encrypt, we have to have this mapping where it takes 000, convert it to ciphertext like that, right? So I need to store both of these columns in a memory. Okay, so for how many bits I need to store this table? Well, 4 bits multiplied by 16 rows. So do 4 by 16, right, for this column alone. And then 4 by 16 for the second column. All right, that's not so bad. But if I have 64-bit here instead of 4, and to have all the combinations, we have 2 to the power of 64 rows. So we'll have to multiply 64 bits here by 2 to the power 64 rows. That will take a lot of memory. So in fact, here to store the mapping, we have to have n multiplied by 2 to the power n bits. So that's for n equals 64, that's 64 multiplied by 2 to the power 64, that's 2 to the 70 bits. 2 to the 70, now remember, for each, so if we consider 4 gigabyte of RAM, that's 2 to the power of 35. That's just, and to add, so if we use a PC that has 4 gigabyte of RAM, that will give us 2 to the power of 35. Every bit to the exponent we add, that's another 4 gig, right? So 2 to the power of 36, that's another 4 gig, right? So the number of PCs that we need to store the key is 2 to the power 35. Now you cannot find that enough PCs, or you can have a PC with really huge memory, right? Neither one of these options is practical. You cannot just stack 2 to the power of 35 PCs just to encrypt and decrypt. You cannot do that. Neither can you have a PC with this such large memory here just for encryption and decryption. So we need some kind of better techniques other than the mapping. You could simply say, well, how about we use hardware like this? Okay, so yeah, some of the techniques that we uses hardware, but the hardware, remember this, the key is embedded. So these wiring, we cannot change them if we use hardware. The mapping is fixed. So this means that if we build the hardware, the key is always fixed. So one of the techniques, so using hardware is not the uh, is not practical either, right? So before we move on, um, now we have a solution, obviously, we just didn't get there yet. So, but before we get to that solution, which will be in the next chapter, we need to consider this concept of diffusion and confusion. Um, so each one of these terms means something. So the diffusion is intended to hide the relationship between the ciphertext and the plain text. What I mean by that is when you go back to Caesar, right? Caesar did not hide the the relationship between the ciphertext and plain text. For example, the ciphertext has the same size as the plain text, right? 5 characters will be translated into 5 characters. Every letter will be translated to the same letter, or when we convert A, it's always converted to same character in the ciphertext. So this means that um, the common letters in the plain text will be common also in the ciphertext. So the relationship, it's there, right? We didn't hide it. If there is a word that repeats continuously, like the in English, we will find it in the ciphertext as well, just different characters, right? Maybe not THE, but we will find 3 characters being repeated all the time, right? So that's what we will call a relationship between the ciphertext and plain text. The purpose of the diffusion is to hide this relationship. So if somebody looks at the ciphertext, they won't figure out a direct relationship to the plain text. We achieve that by doing substitution and transposition, right? So the techniques that we talked about earlier, we use them so that we hide the relationship between the ciphertext and the plain text. By substitution, we convert the letters. By transposition, we move them around. So the THE, it could be translated to 3 other letters, but they will be broken apart. They won't come, you won't see the cipher equivalent of THE everywhere. No, they will be broken apart by the substitute, by the transposition. All right. So that's the concept of diffusion. So there is this uh, another person, uh, Polybius, if I pronounce it correctly, came with came up with this cipher that translates the characters into numbers, um, and then so that's substitution, and then moves them around so it does transposition. So it does both things. So um, so if we take English alphabet again and we arrange it into 5 by 5, the problem with the English alphabet is it's 26 characters. 26 characters we can split them into 3 by 12, right? So we can do 3 by 12. Um, maybe we can, what else we can split 3 by 12? Um, maybe different arrangement will work. Maybe 6 by 6 won't work. So 3 by 12 will give us exactly 26 characters. But if we arrange them in 25 by 5, we have to lose a character. We have to lose a letter. So sometimes, actually, in cryptography, as we saw earlier, um, we don't have to stick to the spelling, right? The correct spelling we saw that we skipped the letter, so we wrote it as RITE instead of WRITE. So English has the I and J are similar, so we could just use one of them instead of the two. So now we reduce the number of letters from 26 to 25. Some students are puzzled by this and they keep asking me why. It's just the reason is just so that we can arrange the letters in nicely 25 by or 5 by 5 matrix, right? Uh, Instead of otherwise we will have to arrange them in 13 by 2, so we don't have to stick to exactly 26. And we can misspell some letters, so what? Uh, the purpose here is not correct grammar or spelling. The purpose here is to make sure that nobody looks at our encryption. So this person arranged the letters in 5 by 5 matrix. So A, B, C, D, E, F, G, H, and I and J, combine them together, K, L, M, and O, and so on, right? And to encrypt a message, let's say Jester here, you can go to J and write the 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 number in the column here and the number in the row here. So that's 24 to represent J. So now I substituted a letter with a number, right? E, well, E is here. So now we can substitute it with 15. And S is 43. And T is 44, and so on. So I replaced the gesture here with this sequence of numbers. So that's substitution. And then we do transposition. So if I write each number here as two rows, so 24 is 2 top, 4 bottom, 15, 1 top, 5 bottom, and 43, and so on, then write the 21, 44, 14, 45. So now I write the ciphertext will be each two characters or each two numbers. So I'll write them row by row. So 21, 20, 44, 14, 45, 34, 52, right? So now I did both substitution and transposition. So that is the technique that uses both. So as I said before, the diffusion here is supposed to hide the relationship between the cipher and the plain text. There is also another concept which is called confusion. The goal of the confusion is to actually prevent the the attacker from figuring out the key. Okay. Back to the cipher, the original Caesar cipher. Somebody looks at the message, they can find the key much easier, right? Just try to shift the characters left and see if the result of the shift makes sense. But if one of the techniques or one of the things that the cryptographers want to achieve is to hide, is to prevent somebody from looking at the text, the ciphertext, and figuring out the key, right? So confusion hides the relationship between the ciphertext and the key. Okay, so the last thing we want to talk about is the kind of techniques that the cryptanalyst will do, or the attackers or the hackers will do to break the encryption, to decipher the ciphertext. So we have three techniques. So if somebody get their hands on the ciphertext only, right? Just figuring out what, so they, and that's actually one of the easiest thing to do, right? If I sniff the traffic in the network and I capture the ciphertext, or if I see a document written, you know, uh, encrypted in front of me, I will have only the ciphertext in front of me. One of the things that I can do is to do the um, pattern analysis. The pattern analysis will look at all, will analyze the text and say, well, what is the most common letter? What is the most common word? If the most common letter in the ciphertext is R, and I know this is English, then okay, that must correspond to E because the most common letter in English is E. That's one technique. Another technique could be by using brute force attack. Brute force attack will try all the keys, especially if I have a limited number of keys. I can try them all. Now, one of the techniques that the hackers try to do is to collect as much ciphertext as possible, right? Because sometimes the challenge is not finding key, but the challenge is, let's say, the word. I try to uh, find the key using something that was encrypted using cipher, Caesar cipher, and X, Y, and Z can be translated into THA by shifting certain characters. It can also be translated to cat or hat, right? So if you take X, Y, and Z and shift it by a certain number of characters, I'll let you find out how many characters you need to shift, but you will end up with that. If you shift it by another set of by another number, you may get cat, or you may also get hat. So which one is correct? Now, if the message is short, I may not know which one is the correct key, which one is the one that actually, the key that actually solves the problem. But if I have large, large um, database of ciphertext, now I will figure out, because from the message you will figure out whether the XYZ represents actually the or cat or hat by the context. If you're talking about animals, you probably will, cat makes sense. If we're talking about clothes or weather, hat make more sense. So one of the things to prevent such an attack is to make sure that the attacker does not get a lot of ciphertext, right? So if they put their hands on the ciphertext, they don't get a lot of them. Actually, some of the countries right now they don't know how to decrypt messages, but their attack uh, aimed at collecting as much ciphertext as possible, because they know in the future that the technology will advance, the computers will be much faster, so they will collect ciphertext now, even though they cannot break it now, but they will break it in the future. So why do you want to break? Does it make sense to save something now to break it in the future? Well, sometimes some secrets became or still useful 50 years from now, right? Some they have no need. Let's say you encrypted a message to your bank asking for a loan, right? All right, 10 years from now, so what, somebody discovers that you asked for a loan or you ask for a transaction moving money from one bank on another. So at some point, uh, this information becomes useless, even if somebody figure it out. But some secrets are still significant, even long time from now. And so some of the attackers are actually trying to collect as much ciphertext possible for now to break it in the future. In general, um, the less ciphertext the attacker has, the better, right? Another another technique or another type of attack is called the known plain text attack. So the known plain text attack is um, where you get actually both. You get the plain text and you get the ciphertext. But that becomes a problem. If I know what is the ciphertext, let's say I know that cat in the plain text equal XYZ in the ciphertext, then it's very easy to find the key, right? Especially with the monoalphabetic ciphers, because I know that every character transpose or transforms it into another character. It is more difficult for other techniques, but it's not uh, impossible. So it is. So how does somebody have or get their get their hands on the plain text and the ciphertext at the same time? Well, if somebody is um, sniffing traffic, um, and we'll see in later courses that there are techniques where there is a challenge. So the server will send you a message and say, well, encrypt it for me using the known technique that we talked. Actually, we may even discuss it in this course. So the client will encrypt that message and send it back. So if you are listening or sniffing traffic, you will get your hand on both the plain text and the ciphertext. Uh, So some of the communication protocols will try to or attempt not to provide the attacker with the opportunity of getting their hands on both. Sometimes we don't even need that. Sometimes, let's say, I guess in the World War II, there were one way for or one clue the Allied had and used to break the system is knowing that the Germans always start their report by certain greeting or certain code. Every time they send a message in secret, they will start the message by, let's say, dear sir, right? And you will start and you'll write the message underneath, dear sir, or you end it with, best regards. If you know that the message always starts by these dear sir characters or the date or any pattern, now you know the plain text. You just need to know that the start of the message is the cipher. So you compare, all right, I know that this dear text, dear sir, is equivalent to YZWR, right? So now I have the plain text and the ciphertext. And this is how they figured out or they broke some of the codes. The final attack is what's called the chosen plain text attack. In that case, the attacker actually sends the server the plain text that they choose. So let's say there is a kind of attack on a server where the attacker knows that every time they send a plain text, the server will encrypt it and send it back to them. And we'll see examples of that maybe later. So great. So all the attacker can do is to send any message that they want to the server, and the server will reply that with the encrypted message. So the attacker now can sit and collect a database of information where they have a text of their choice and the equivalent ciphertext. And then later, if they want to decrypt something, they will just go and look at the message that they want to decrypt and look at their database of all these messages that they collected, and they find uh, the plain text. Now, all of these techniques work very easily on the monoalphabetic ciphers. And as I said before, the 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 goals of the cryptography and the cryptography algorithm is to do confusion and diffusion, both. The diffusion eliminates or hides the relationship between the plain text and the ciphertext, and confusion hides the information or hides the relationship between the ciphertext and the key. So the latter, actually, even if you start collecting information, so you send plain text and you receive ciphertext, that may not be enough to find the key. Why? Because the relationship between the cipher and the key is vague. So in the ideal uh, algorithm will use both confusion and diffusion um, to basically to prevent all these kind of attacks. Right? So finally, what we will study uh, for the rest of this course is three kind of cryptography functions, and we'll order them based on how many keys they need. So we looked at cryptography or described cryptography techniques that use one key, right? We'll call these secret key cryptography techniques or private key cryptography uh, or secret key functions. There is also cryptography techniques that doesn't have any key, right? So because they don't have any keys, they are not it's not possible for anybody to decrypt the message. Once we encrypt it, it cannot be decrypted. So they can be used for other purposes, not for encryption and decryption, but we can use them for integrity checks and for authentication. So these we'll call them hash functions. And then there are the modern era techniques, and using more understanding of math, there was also the invention of public key cryptography. Public key cryptography uses two keys. We can encrypt with one key and decrypt with another. And these have a lot of applications in networking, right? In fact, uh, we use them almost not only daily, but hourly or every minute. Every time you go and uses HTTPS server, you are actually using public key cryptography. So we will talk about these techniques there's a chapter for each one of them, and we will start with the most common, which is the secret key cryptography. So until then, thank you for listening, and we'll see you in the next recording.